Welcome back. This will be a short video lecture on Section 2.1, Introduction to Systems of Linear Equations. This is a short section, so I will do this in one installment. And in this video lecture, we will cover linear equations, systems of equations, equivalence systems, and finally, augmented matrices. Let's begin with linear equations. So what is a linear equation? Before I give you a formal definition, let's look at some examples. So the equation 3x plus 4y minus z equals 16 is a linear equation in the variables x, y, and z. Notice that the variables are not mixed and they appear only to the power of 1. The equation 5 over x plus 4xy plus 5z equals 38 is nonlinear. There's two things here to notice, right? The variable x is appearing to the power of minus 1, and the variables x and y are mixed. So here's the formal definition of a linear equation. So a linear equation in the variables x1, x2, up through xn is an equation that can be written in the form a1 times x1 plus a2 times x2 on out to an times xn equals b, where the coefficients, the a1, a2 up through an, and the constant term b are all constants. So think of those as some numbers that have been expressed. So in other words, another way to think about this is that if I take all the coefficients and put them into a vector of length n, and I take my unknowns x1 through xn and put them into a vector of length n, we can think of a linear equation as being expressed as a dot x equals b. So in other words, this left-hand side here can be expressed as the dot product of a vector of coefficients and the vector of unknowns. And so this will be our conception of a linear equation. It's often helpful to think of a linear equation geometrically. So in two variables, a linear equation is just the equation of a line, and in three variables, a linear equation is just the equation of a plane. In general, a linear equation in the n variables produces what's called a hyperplane in n-dimensional space. Now, what is a solution to an equation? The vector x, y, z equals 1, negative 1, 3 is a solution of the equation 2x minus 3y plus 3z equals 14 because when I plug in x equals 1, y equals negative 1, and z equals 3, I get a true statement. 14 equals 14 is true. Now, the vector x, y, z equals 7, 0, 0 is also a solution of equation 1. Why? Because 2 times 7 minus 3 times 0 plus 3 times 0 is also equal to 14. However, the vector x, y, z equals 1, 5, 2 is not a solution of the equation. When I plug in x equals 1, y equals 5, and z equals 2 into the left-hand side, I get negative 7. And since negative 7 does not equal 14, this, in fact, is not a solution of equation 1. Our next topic is systems of equations. A set of linear equations in a common vector x1 through xn of variables or unknowns is called a system of equations. So here is a system of equations in the variables x, y, and z. Our first equation is 2x plus 3y equals 6. Our second equation is x minus y plus 2z equals 15. Our third equation is y plus 3z equals 18. So first notice that each of these equations is a linear equation in the variables x, y, and z. The second thing I want you to notice is that even though the variable z is not appearing here in the first equation, nor is the variable x appearing here in the last equation, that's not a problem because we can always imagine that z is appearing here in this first equation, for example, with a coefficient of 0. So that is not a problem. Now, one thing I want you to do, just to this is a good practice, a good habit to get into, especially as I think about where we're headed. It's very good to, when you're writing your linear equations, your system of equations, to stack the variables on top of each other when you express your equation. So here I have the variables x stacked in the first column, the y's in the second column and the z's in the third column, and I try to keep them in the same order as my vector of unknowns or my vector of variables. Now, you'll notice that here we have equations in three-dimensional space, and each of these is the equation of a plane, so we can attach a geometric meaning to this system of equations. We are being asked to think about a set of three planes in three-dimensional space, or R3. A vector u is called a solution to the system, provided that it is a solution to every equation of the system. In other words, if you have produced a solution to the system, that means that when you plug it into each and every equation in the system, you get a true statement. Now, to solve a system of equation means to describe the set of solutions to the system of equations. And in some sense, this is the beginning of our journey, to describe solutions to systems of equations. Now let's discuss the geometry of solutions. Here's a system of equations in the variables x and y. 2x plus 3y equals 7, and 8x plus y equals 17. Each of these is the equation of a line in two-dimensional space, and we can see these lines pictured below. Now, a solution to the system of equations is a vector xy that simultaneously satisfies both equations. In other words, it would correspond to a point of intersection of these two lines. And when we look at the graphs of these two lines, we can see that they only intersect at the point 2, 1. So the solution in this case is unique, and it's the vector xy equals 2, 1. For our next example, we'll consider two equations in three unknowns, x, y, and z. Our first equation is x plus 2y minus 3z equals 12. Our second equation is 2x plus y plus 3z equals 8. And each of these is the equation of a plane in three-dimensional space. Now, these two planes will actually intersect in a line, which I've represented in this figure below by this line labeled M. So the set of solutions is a line in three-dimensional space, and in particular, this means that there are going to be infinitely many solutions to this system of equations. For our last example, let's consider a set of two equations in the unknowns x and y. Our first equation is 3x plus 4y equals 24, and our second equation is 6x plus 8y equals 20. Now in this case, each of these is a line in two-dimensional space, and it turns out that these lines are parallel. In fact, they will not intersect at all, and so this system has no solutions. A system of linear equations is called consistent if it has at least one solution. A system with no solutions is called inconsistent. So if we look back at our previous examples, this would be an example of a consistent system because it has at least one solution, in this case, a unique solution. This system is also consistent, even though it has infinitely many solutions. Our third example, though, is an example of an inconsistent system. It has no solutions. Now, if a system of equations is consistent, that means if it has solutions, then it has either a unique solution or infinitely many solutions. So for example, once you know that a system is consistent and it has two solutions, it must have infinitely many solutions. Our next topic is equivalent systems. Two systems of linear equations are called equivalent if they have the same solution sets. Now, here's an example of that. In our first system, we have two equations in the two unknowns x and y. And in our second system, we have two equations in the two unknowns x and y. Now, it turns out that each of these systems has one and only one solution, namely x equals 1 and y equals 3. So these systems are considered equivalent, therefore, because they have exactly the same solution set. This notion of an equivalent system is incredibly important and powerful. Let's remember that our goal is to take a system of equations and describe its entire solution set. Now, what I'm going to show you is a sequence of operations that we can perform on systems of equations that will return equivalent systems. So if our goal is to describe the solution set of the original system, it's enough to describe the solution set of the equivalent system. Now, there are three basic operations on a system that produce an equivalent system, and I will call these type 1 or switch, type 2 or scale, and type 3, which is a copy, a scale, and then an add. So let's look at each of these in some detail. Let's look at type 1 or switch first. So switching a pair of rows in a system always produces an equivalent system. So for the example I've worked out here, I've got x plus 2y equals 4 and 3x plus y equals 7. That's my system here on the left. Now what I'm going to do is switch the rows. I'm going to replace row 1 by row 2 and row 2 by row 1. I'm going to notate that this way. And so my new system is going to read 3x plus y equals 7 and x plus 2y equals 4. These systems are absolutely equivalent to each other. Any solution to the system on the left is going to be a solution to the system on the right, and vice versa. So our first type of operation is going to be called a switch or a type 1 operation. Our next basic operation is a type 2 operation or a scaling. So scaling a row in a system by a non-zero number produces an equivalent system. So let's take a look at our example here. On the left, we have two equations and two unknowns. The first equation is x plus 2y equals 4. The second equation is 3x plus y equals 7. Now in this operation, I'm going to take row 2 or equation 2 and multiply it by 3. And so this is how I'm going to notate that operation. 3 times row 2. Now that'll have no effect on the first row or the first equation. It's still x plus 2y equals 4. The second equation, however, is going to be magnified or scaled by a factor of 3. We now have 9x plus 3y equals 21. Now, it's easy to see why the system on the right is equivalent to the system on the left, because, in fact, this is just a re-representation of exactly the same line. So the line 9x plus 3y equals 21 is exactly the same line in space as 3x plus y equals 7. It's just being represented differently. It's been scaled by a factor of 3. So this type 2 operation, the act of scaling a row or an equation by a non-zero number, always produces an equivalent system. Our next operation is called a type 3 operation or a copy, scale, add operation. It is the most obscure of the three. So let's see if we can get the hang of this. Let's take a look at this system of two equations and two unknowns. X plus 2y equals 4 is our equation in row 1, and 3x plus y equals 7 is the equation in row 2. Now, in our example, we will make a copy of row 1, scale it by a factor of 3, and then add it on to row 2. So the important thing to understand here is that I'm using row 1 to have an effect or to make an effect on row 2. So we're going to retain the original row 1 when we form our equivalent system. We're not going to be changing row 1 at all. So this will appear intact in our equivalent system. Now, all of our changes are occurring to row 2. Remember, we're making a copy of this row, scaling it by 3, and tacking it onto this row. So let's see what that's going to look like. Now, on the left, we'll still have the 3x plus y. That's still going to be there. But we'll have magnified this part by 3. So on the left, we will also see an additional 3 times x plus 2y. Now, on the right, we're still going to have the 7. That's still there. But we will have tacked on an additional 3 times 4. Now, when we work this out, let's work this out. What's going to appear on the left? We're going to have a 3x combining with the original 3x to give us a 6x. And we'll have a 6y combining with a y to give us a 7y. So on the left, we're going to have 6x plus 7y. Likewise, on the right, we're going to have the 7 plus an additional 12 or a 19. So our new system of equations is going to be x plus 2y equals 4 and 6x plus 7y equals 19. Here's what this operation would look like in context. On the left here, I have my original system of equations. Now I'm going to do a type 3 operation on this system, and in this case I'm taking 3 times row 1 and adding it onto row 2, and that's how I will notate the change that I'm making. Now remember, I'm working with a copy of row 1 and I'm having an effect on row 2, So when I look to the right here, I will see exactly the same row 1. I will see x plus 2y equals 4. And here in row 2, I will see my altered row 2. I will see the effect of this type 3 operation on row 2. Now, the new system is equivalent, but it's important to understand that whenever I do a type 3 operation, I am altering the geometry of the system of equations. So in a type 1 or a type 2 operation, I'm not fundamentally altering the geometry of the system of equations. But anytime I do a type 3 operation, I am altering the geometry of the system. I'm not changing the solution set, but I am altering the geometry of the system. So let's take a look at that at the Desmos graphing calculator. So now let's take a look at the original system of equations. X plus 2y equals 4 and 3x plus y equals 7. We can see these lines graphed over here. We can see they intersect at the point 2, 1. That's the solution to the system of equations. X equals 2 and y equals 1. Now what we're doing is we're exchanging this second equation for 6x plus 7y equals 19. So I can add that line in, and I can take this line out, and we can see that we've altered the geometry of the system of equations. This is not the same set of equations. Nonetheless, it retains exactly the same solution set. So that's the idea behind a type 3 operation. I'm not making the claim that the lines are the same, but I am making the claim that the solution set has not been altered, that we still have an equivalent system of equations. Let's work a problem together. Let's use equivalence to solve the system of equations. Our first equation is 2x minus 4y equals negative 10, and our second equation is 4x minus 6y equals negative 12. So join me at the document camera, and I'll show how we can use equivalence to solve this system of equations. Welcome to the document camera. We're going to solve this system of equation using our type 1, type 2, and type 3 operations. Now, what I'm going to do first is I'm going to multiply this first row by 1/2 so that I can turn this coefficient of x into a 1. So my first operation is going to be to take 1/2 of that first row. Now that's going to change all of the coefficients in that first row. I'm going to have x minus 2y equals negative 5. Row 2 is going to be unchanged. Now I'm going to use a type 3 operation here. I'm going to use this 1x here. I'm going to use it to eliminate this 4x in this equation here. So my type 3 operation is going to be to take row 1 times negative 4 and add that on to row 2. Now remember, this is only affecting row 2. Row 1 has been copied, scaled, and added on to row 2. So I'm going to keep the original row 1, and I'm now updating row 2 according to this recipe. So place by place, I have to multiply by negative 4, so that's going to be negative 4x. That's going to be added onto the 4x. That's going to give me 0x. I'm going to write it in there just so you kind of know that we processed it. Now I'm multiplying by negative 4, so that's going to turn this into 8y. 8y added onto the negative 6y is going to give me plus 2y. I'm multiplying the negative 20 by negative 4. I'm multiplying the negative 5 by negative 4, so I'm going to get 20. 20 added on to the negative 12 is going to be 8. Now I could stop here, but I'm going to do one more operation. I'm going to scale this so that this coefficient is equal to a 1. So I'm going to do 1/2 row 2. Again, row 1 is unchanged. And now I'm going to have y equals 4 in place of equation 2. And I'm going to stop here. Now later in the course we'll take this even a little bit further, but I'm going to stop my analysis here because I now have, if we believe everything we've been studying, every time I do one of these elementary operations, I'm always getting an equivalent system. So the claim is that whatever the solution set to this original system is, it's the same as the solution set to this system. But we've now reached a place where we can quickly realize what the solution set to this system is. We now know that y is equal to 4. And if y is equal to 4, we can read this equation and substitute in y equals 4. And so that says x minus 2 times 4 equals negative 5, or x minus 8 equals negative 5, or x equals 8 minus 5, or 3. So we now have a complete solution to the system of equations. We know that this system is solved by x equals 3 and y equals 4, and by equivalence, we know that this system is solved by x equals 3 and y equals 4. So that's how we can use this notion of equivalence and these elementary operations to slowly take our original system down into something where the solution basically just reveals itself to us. Okay, let's head back to the course notes because I want to show you one additional thing that we can do to simplify things. Our last topic is augmented matrices. An augmented matrix is simply a way of encoding a system of equations. Let's take a look at this example here. Here I've got two equations and two unknowns, and before I encode this system in an augmented matrix, I just have to make sure that a couple of things are in place. I want my equations, I want all the variables to be on the left and the constants to be on the right. Next, I want to make sure that my variables are stacked in columns. So I'll have a column for the x variable and a column for the y variable. Once I've got that in place, I can simply lift out these coefficients and constants and place them into this rectangular array on the right. So I preserve their positions, the relative positions to each other. So in this first row, I'll have the 2, the negative 4, and the negative 10. And in the second row, the 4, the negative 6, and the negative 12. And the convention is to replace this equal sign by a vertical bar. So this vertical bar is separating the coefficients from the constants. So that's how we encode in this direction. To unencode this, to take the augmented matrix and reverse the encoding, right, is simply to take these as the coefficients of x and y, and these as the constants. So if I see this first row, I can read that simply as 2x minus 4y equals negative 10, and 4x minus 6y equals negative 12. So I can take a system and put it into an augmented matrix, and I can take an augmented matrix and retrieve the system from which it came. Okay, now the beauty of this is that if we think about it, our type 1, type 2, and type 3 operations ultimately are changes that are being made to the coefficients and the constants in these linear equations. And so what an augmented matrix is allowing us to do is simplify the look of the system of equations and concentrate all of our energies on updating the coefficients and the constants through these type 1, type 2, and type 3 operations. Now, let me show you. Let's solve the system of equations x plus 2y equals 9 and 3x plus y equals 12 through its augmented matrix. So we're still going to use our row operations, but we're now going to use them on the augmented matrix. So let's go over to the document camera and see how to encode this and how to work out the solution through the augmented matrix. Welcome back to the document camera. We're going to solve this system of equations now using an augmented matrix in conjunction with our type 1, type 2, and type 3 operations. So first, let's encode this in an augmented matrix. So we're going to check we have our constants on the right, variables on the left. We've got our variables stacked. And so we can simply exchange the system of equations for this augmented matrix, which will be 1, 2, 9, 3, 1, 2. All right, that's the first step to get the augmented matrix. And now we're going to apply our type 1, type 2, and type 3 operations to this augmented matrix, to this system. And normally what I'd want to do is I'd want to get a 1 in this position, and it already is a 1. And now what I'm going to do is, as before, I'm going to use this 1 in conjunction with a type 3 operation to eliminate this 3 that sits below it. So my action is simply going to be take negative 3 times row 1 and add it on to row 2. So you have to keep your eye on the prize here. We're trying to make this into a 0. So I'm going to do negative 3 times 1, add it on to row 2. That's going to turn this position into a 0. Now it's going to have an effect elsewhere, but this is the main effect that we want. We want this position to be a 0. So let's take a look. Let's remember that row 1 is not changing, so I'm going to rewrite the 1, the 2, and the 9. And now I'm simply going to multiply by 3 and add down in each of these positions. So minus 3 added onto the 3 gives me a 0. A minus 3 minus 3 times the 2 is a negative 6. Added onto the 1, it's going to be a negative 5. Now I'm doing a negative 3 times the 9. That's a negative 27. Added on to the 2 is a negative 25. Now I could stop here, but I'm going to clean up the system a little bit. I'm going to turn this position into a 1 by multiplying by a negative 1/5. So I'm going to scale row 2 by a negative 1/5. So our new row 2 is going to look like this. Again, row 1 is not changed, but our new row 2 is going to be 0, 1, and when I multiply this by negative 1/5, I'll have 5. Now at this point, we can decode this or unencode this. We know that this row corresponds to the equation, right? If we remember, this is the x column and this is the y column. This second equation says y equals 5. And so we know that y is equal to 5. And then when we go back into this first row, we know that that reads x plus 2y equals 9. But y is equal to 5. So x plus 2 times 5 equals 9. So x plus 10 equals 9, or x equals negative 1. Okay? Now that's the solution to our final system of equations, and by equivalence, it's the solution to our original system of equations. Let's work one last problem in this section. Here we're going to work on a system of 3 equations and 3 unknowns. And let's head over to the document camera. We'll encode this in an augmented matrix, and I will show you how we can use our type 1, type 2, and type 3 operations to produce an equivalent system that can be easily solved. So join me over at the document camera for the exciting solution to this system of equations. All right, welcome back to the document camera. I've taken the liberty of putting our system of equations into its augmented matrix. So I've saved us the problem of encoding that system into this augmented matrix. Now, let's concentrate on reducing this system using these type 1, type 2, and type 3 operations. The first thing I'm going to do, and this is typical, I'm going to turn this position into a 1 by scaling row 1 by a 1/3. So I'm going to multiply row 1 by 1/3. And a lot of times what I like to do is just to rewrite quickly the rows that aren't changing, just to remind myself that row 2 and row 3 are not being affected by this. So I'm going to rewrite those rows right away. And that way I can kind of concentrate on the only part that's changing. So everything in row 1 is going to be scaled by 1/3 or multiplied by 1/3. So I'll end up with 1, 2, 8, and 17. Okay, now my next move is to use this 1 that I've created here to eliminate the 1 that sits below it. So what I'm going to do is I'm going to take a -1 times row 1 and add it on to row 2. Now let's think about this. Row 1 is not changing, so I'm going to rewrite that one right away. And row 3 is not changing, so I'm going to write that one right away. And now I'm going to concentrate on the changes that are going to be affected in row 2. Now remember, I'm using row 1, so I'm multiplying by -1 and adding down. So -1 times 1 added down is going to give me a 0 in that position. Minus 1 times 2 added on to 4 is going to give me a 2 in that position. Okay, minus 1 times 8 is going to be negative 8 added on to 14 is going to give me a 6 in that position. And then finally, minus 1 times 17 added on to 27 is going to give me a 10 in this position. Okay, now I'm going to use this minus 1, or excuse me, I'm going to use this 1 here to eliminate this 2 here. So I'm going to do negative 2 times row 1 added on this time to row 3. So there's no effect. No effect is going to be witnessed in row 1 or row 2. So I'm going to rewrite those rows right away. But I am going to see a change in row 3 according to this recipe. So I have to take row 1, multiply it by negative 2, and add that on to row 3. So I'm going to see a minus 2 times 1 added on to the 2. So minus 2 times 1 added on to the 2 is going to give me a 0 there. That's what I wanted. Minus 2 times 2 is negative 4. Added on to 4 is going to give me a 0 here. And negative 2 times 8 is going to be a negative 16. Added on to the 17 is going to give me a 1 in this position. And then negative 2 times 17 is a negative 34. Added on to 36 is going to give me a 2 in this position. Now, this is a great place to stop. Let's think about why this is a good place to stop. Because, and this is what's usually called echelon form. I've got this kind of staircase form here. If you notice in equation 3, right, if I think of these as x, y, and z, equation 3 is saying that z is equal to 2. Okay? Now look at this. Because equation 2 only involves y and z, I'm one step removed from being able to evaluate y. So this equation 2 is saying 2y plus 6z is equal to 10. So that means that 2 times y plus 6 times 2 equals 10. I'm substituting in z equals 2. And so that says 2y plus 12 is equal to 10. 2y is equal to negative 2. Or y is equal to negative 1. Okay, now I've got values for y and z, and now I can go back to equation 1, which is giving me x, y, and z, so x plus 2y plus 8z equals 17. But now I have values for y and z, so I can finally solve for x through this process of back substitution. So I've got x plus 2 times negative 1 plus 8 times 2 is equal to 17. So that's x minus 2 plus 16 equals 17. X plus 14 equals 17. Or x equals 3. Okay? So if you think about what we've done a sequence of type 1, type 2, or type 3 operations. So in each stage, we're getting an equivalent system. But our goal has been to kind of get things down into this echelon form. Once we're in this form, we can use this process of back substitution. We can solve for z trivially in this third equation, use that to solve for y in the second equation, and then use that to solve for x in this first equation. And so that's how we can use our augmented matrices, our type 1, type 2, and type 3 operations to slowly whittle away at our original system of equations and get it into a position where we can quickly solve it through this process of back substitution. All right, that brings a close to this section, and I hope you enjoyed this. I will see you again for some lectures on section 2.2.